NLDA1. In the first approach, which is referred to as NLDA1, the transformed features are produced from the final output layer of the network. This approach is similar to the use of tandem neural networks used in some automatic speech recognition studies, Hermansky and Sharma, 2000, Ellis et al., 2001. Illustrates the use of network outputs in NLDA1. Use of network outputs in NLDA1. NLDA2, who? Since the activations of the middle layer represent the internal structure of the input features, in the second approach named NLDA2, the outputs of the middle hidden layer, with fewer nodes than the input layer, are used as transformed features to form reduced but more discriminative dimensions. Illustrates the use of network outputs in NLDA2. These two versions of NLDA were experimentally tested, with and without PCA following the neural network transformer, with some variations of the nonlinearities in the networks. The dimensionality of the reduced feature space is determined only by the number of nodes in the middle layer. Therefore, an arbitrary number of reduced dimensions can be obtained, independent of the input feature dimensions and the nature of the training targets. A lower dimensional representation of the input features is easily obtained by simply deploying fewer nodes in the middle layer than the input layer. This flexibility allows dimensionality to be adjusted so as to optimize overall system performance. Huanzarian, 2008, Huanzarian, 2009, Huanzarian, 2010. In contrast with NLDA1 where dimensionality reduction is assigned to PCA, for NLDA2, since the dimensionality reduction can be accomplished with the neural network only, the linear PCA is used specifically for reducing the feature correlation. Middle layer outputs used as dimensionality reduced features in NLDA2. Neural networks. In optimizing the design of a neural network, an important consideration is the number of hidden layers and an appropriate number of hidden nodes in each layer. A neural network with no hidden layers can form only simple decision regions, which is not suitable for highly nonlinear and complex speech features. Although it has been shown that a neural network with a single hidden layer is able to represent any function with a sufficient number of hidden nodes, Duda et al., 2001, the use of multiple hidden layers generally provides a flexible configuration such as distributed deployment of hidden nodes, and diverse nonlinear functions for different layers. On the number of hidden nodes, a small number reduces the network's computational complexity. However, the recognition accuracy is often degraded. The more hidden nodes a network has, the more complex a decision surface can be formed, and thus better classification accuracy can be expected. Ming, 2006. Generally, the number of hidden nodes is empirically determined by a combination of accuracy and computational considerations, as applied to a particular application. Another important consideration is selecting an activation function, or the nonlinearity of a node. Typical choices include a linear activation function, a unipolar sigmoid function and a bipolar sigmoid function as illustrated in. The activation function should match the characteristic of the input or output data. For example, with training targets assigned the values of 0 and 1, a sigmoid function with the outputs in the range of is a good candidate for the output layer. Most typically a mean square error, between the desired output and actual output of the NN, is the objective function that is minimized in NN training. As another powerful approach, the softmax function takes all the nodes in a layer into account and calculates the output of a node as a posterior probability. When the outputs of the network are to be used as transformed features for the HM recognition, a linear function or a softmax function is appropriate to generate the data with a more diverse distribution, such as one that would be well modeled with a GMM. Moreover, equipped with various nonlinearities, the neural network is expected to have a stronger discriminative capability and thus it is enabled to cope with more complex data. Illustrations of a linear activation function, left, a unipolar sigmoid function, middle, and a bipolar sigmoid function, right. The weights of the neural network are estimated using the backpropagation algorithm to minimize the distance between the scaled input features and target data. The update of the weights in each layer depends on the activation function of that layer, thus the network learning can be designed to perform different updates when dissimilar activation functions are used. In addition, a difficulty in neural network training is that the input data has a wide range of means and variances for each feature component. In order to avoid this, The input data of neural networks is often scaled so that all feature components have the same mean, 0, and variance, so that range of values is approximately plus or minus 1.